Okay, so we're going to split up lesson 2.5 into 2 days and just, take it kind of one bite at a time, if you will. We're going to start off with just a general idea of what it means to be a compound inequality and how we solve compound inequalities. That's the main focus today. So yes, we're still going to solve, but we're going to look to see how we do that when we have compound inequalities. So you might be asking, well, what does that mean? So I'm going to start with that. So essentially, a compound inequality a compound inequality is an inequality that is formed by joining two inequalities with the word either and or the word or. Okay, so essentially the idea here is that these inequalities, they contain more than one limit or more than one criteria. We've had a few like this actually already. For example, I'm going to pull our notes from a day or two ago when we were solving here number 12. We set up our inequality based on area, we solved for it, and we realized that the values that made sense here were x values that were greater than 4, right? Well, you might make an argument that, sure, that makes sense, but there might be, an upper limit here. The infinity isn't really going to be a realistic side length. The scenario might have been that, maybe the property itself is no more than 100 feet by 100 feet. So there might be another limit. It might be really all the x's that are greater than 4 but less than 100 feet, for example. So in situations like that, when you have more than one boundary or more than one limit, that's when we tend to use this concept of a compound inequality instead. And so we're just going to observe how that plays out here and how, if anything, what we have to do differently for that. So let's get started. Let's first talk about the and statements. So the graph of a compound inequality that has the and statement, okay, is essentially what we call the intersection, okay, of the graphs of two inequalities. And the graph shows the numbers that are solutions for both. So when it's an and statement, then our solution is basically where each individual inequality intersect, and only the region that is true for both is then a solution to the compound statement. So let's say that one of my criteria is all the x's that are greater than or equal to 2. So that by itself would be graphed right here. All the x's that are greater than or equal to 2. There's that, okay? But then I add another limit that says I also need those x's to be less than 5. So this is the individual graph for the first inequality. This is the individual graph for the second inequality. If I want to create a compound statement out of those, and say, hey, I really am only interested in the x's that are both greater than or equal to 2 and less than 5, then it limits or it narrows down the choices to this region here where those two graphs overlap or intersect. Essentially, when those values are true for both of the inequalities in the and statement. Okay, so for example, I've got these points over here that are true for this one, but they don't work for the top one, right? So they're only true for one of them. Or maybe, this point right here, which is true for the top one, that's shaded, but it's not true for this middle one, for the bottom one, right? So only in this region where you would consider the two lines intersecting or where they overlap one another, only that region will work if you want the solution to an and statement, because it's got to be true for both. So if I think of the number 3, for example, and I test it, I know that the number 3 is indeed greater than or equal to 2, and it is also less than 5. So I know it is a solution to the compound statement, okay, because it makes them both true. And for the and statement, it's usually essentially a line here with two endpoints. And it's just everything in between the two boundaries. And a lot of times we write it together. So both of these are acceptable. You could write one inequality and then the word and then the other inequality. Or a lot of times we just kind of merge them together into one longer statement where I say, hey, basically x is everything between 2 and 5, including the 2, right? So there's my little or equal to right in here, but it's all the x's that are between 2 and 5, everything greater than or equal to 2 and also less than 5. So it gets merged together as a single statement, almost the same way that the graph does here, and we just are focusing on the part that makes them both true. So both of these are acceptable. Okay, and that is how the and statement works. It's where they overlap. It has to be true for both. It is not enough for it to be true for just one side or the other. It's only the region that's true for both. Okay, the other type of compound inequality statement is the or statement. And the graph of a compound inequality with an or is just the union of the graphs of the inequalities. Okay, and the graph for these guys, it's just going to show us the numbers that are solutions to either one. It does not have to be true for both, as long as it's true for one or the other, okay? A lot of times, not always, but a lot of times these guys are shading away from each other. And if it's an or statement, I'm not interested in them having to be true for both. As long as it's true for one or for the other, we're okay. So we call it the union because it's really just basically the two graphs together. I'm not limiting it to only where they're true for both. As long as it's true for one or the other, it's going to go on my number line. Okay, so you can think of that as like, you know, for this or statement, it's all the y's that are less than or equal to -2, which is this region here, or greater than 1. And so all I'm really doing in an or statement is essentially graphing each one of these, but on one single number line. And I'm not cutting it down to only where they overlap. In fact, a lot of these times, these do not overlap, okay? I just really just include all the numbers that make one of them true and all the numbers that make the other one true. And as long as our values land in either or, then it is a solution to the or statement. It does not have to be true for both. So -2 here is a solution to this or statement because it satisfies at least one of the inequalities in the or statement, okay? +2 is also a solution to this or statement or to this compound inequality because it is true for at least one of these. Okay, so as long as it's true for at least one, either one, then we're good. It does not have to be true for both. So this is less limiting. Notice that for the or statement, especially because they usually shade away from each other, we don't write them together. This is exclusively for and statements. In an or statement, you'll always see the word or in between the two inequalities, okay? All right, so let's just practice setting those up and seeing what they look like, you know, when we're working these out. So if we go ahead and set them up here, make sure I'm not, there it goes, okay. So for number 1, it says, write a sentence as an inequality and then graph that inequality. Well, let's go ahead and first write it. It says a number u is less than 7 and greater than 3. Okay, so this is an and statement. Okay, and I can start off by writing them individually if I'd like. I can say, okay, a number u is less than 7 and greater than 3. So u is also has to be greater than 3. But even better, because it's an and statement, I should be able to merge those together and say, well, basically, you're looking at all the u's that are greater than 3 and less than 7. So everything between 3 and 7. So we can write that then as all the u's that are greater than 3, but less than 7. Okay? Now let's go ahead and graph that. Well, to graph it, let me go ahead and set up my number line here. I'm going to first mark our boundaries. So basically, it's everything greater than 3. So let's start with that 3 boundary. Open circle, because it does not include the 3. Everything greater than 3. So if I just graphed that guy by itself, right, just as an idea, that would basically graph on its own everything starting at 3 and going toward the right. Okay. And it also has to be less than 7. And if I graph this guy by itself, I would need a boundary circle at 7, and everything less than that goes in this direction. Well, in an and statement, my solution is just going to be this region right here where they overlap. Basically, the numbers that make both of these true are everything that is greater than 3, but also less than 7. So we're looking at all of these values between 3 and 7. And I'll write the 3 and the 7 here. I'll just fill this in. Why not? That's not a 3. I put the 3 in the wrong spot. Let's try that again. Boom. Okay. Ignore me. That's what happens when you don't write all the numbers on your number line. See? Teachable moment right here on the video. Okay. There. That's so much. Oh my gosh. Did I put that really on the 3? On the 2? That's it. I am fired. Let's try that one more time. So 0, 1, 2, 3. There's my 3. This never should be this complicated. And this is also why you don't do stuff in ink, but I wanted to make it easier for y'all to see on the video, so I did do ink. So that's why y'all don't do stuff in ink. All right. Oh, so much better now. 3 to 7. So I'm doing everything from 3 to 7. And that's where my final solution. Totally ignore this big flop over here. Everything from 3 to 7, not including 3 and not including 7. They're both open because it's everything less than 7, not less than or equal to, and everything greater than 3. So those boundaries are not included. It's just everything in between them. But all of these numbers, you could test a point, like pick 6, plug it in here, it should work. And then plug it in here, and it should also work. It should make both of them true. In an AND statement, we only want this region right in here that makes both inequalities in the compound statement true. So we're looking at just this, okay? All right, moral of the story, always number your lines properly. Okay, let's try number 2. It says a number D is less than -2 or, so there it is, that's what tells us what kind of statement this is going to be, or greater than or equal to 2. So I'm not going to merge these together. An or statement always stays separate. So a number D is less than -2. So let's go ahead and write that. D is less than -2. Or that number is greater than or equal to 2. Or D could also be greater than or equal to 2. Okay, and really in an OR statement, all we're going to do is graph both of these, but simply graph them on the same number line. So this will feel a lot like less than 2, 1 when we were originally just practicing graphing. And the only difference is that in this OR statement, there are 2 criteria, and we're just going to put them both on the same number line. And as long as it meets one or the other, we are okay. So I'm still going to do a better job at graphing this time, because I'm going to write all of our numbers like that. Lessons learned, right? So one set of solutions that would make this true is any D value less than -2. So I'm going to put an open circle on -2. Less than would be to the left. So any value that fits this criteria will work in this first one, and therefore is a solution to the compound system. Okay? I mean the compound inequality. And then but also any D value greater than or equal to 2 would also work. So I'll put a circle there, closed this time, because it's or equal to. And then anything greater than 2 will also be good and work and be a solution, and, you know, would be a solution to the whole compound statement as well. So anything that fits here or there, as long as it fits in one or the other, would be a solution to this compound inequality. Okay, so this is our compound inequality, and that is how you would graph it. This is our compound inequality, or the top one, and that is almost how you'd graph it, but with less mistakes, hopefully. Okay, let's try number 3, one more. It says a number S is no less than -2.4 and fewer than 4.2. So let's just take it one at a time, and then we'll see about merging it. A number S is no less than -2.4. So that means S is no less than that. It means it's greater than or equal to that -2.4. That's what that means, right? That's one of the criteria. But it also has to meet this other one. So it's got to be no less than -2.4, which means greater than or equal to. And it has to be fewer than 4.2. And this is an AND statement, so it's got to be true for both. we can merge the statement together. By the way, this is something I should have mentioned, but when we merge it together, make sure it kind of follows the same flow as your number line, goes from low to high. So this is the one that essentially will get rotated, and I'll say negative 2.4 is less than or equal to S, which is really, if I look at it kind of this in reverse, it means S is greater than or equal to negative 2.4 and less than the 4.2. So always make sure that your lower one is on the left and you're going up. S is basically everything in between. This should mimic and flow the same way that your number line graph is, is flowing from lowest value to highest value. Okay. So in this AND statement, I need all the S values that are greater than or equal to negative 2.4 and also less than 4.2. So only the stuff that is true for both where they overlap. So as I graph this, okay, I'm going to, see, there I go again. I'm not going to cut these corners anymore. Okay, and then I've got negative 2, 3, 4, 5, and these are all negatives on this side. Okay, so as I start to graph this, I know that I'm going to have a boundary at negative 2.4. Well, be careful here. A lot of people end up putting that right in here, and that would be incorrect, right? I'm going to go negative 1, negative 2, and then negative 2.4 is actually a little further to the left here. This part of it you can eyeball. You can kind of say, well, I think it would land right about there. That's fine as long as it's reasonable. Open or closed circle, I believe that would be close because I want all the x's that are greater than or equal to. As long as it's no less than that, as long as it doesn't go further to the left. Okay, so this might be where my negative 2.4 lives. Okay, and it also needs to be a number less than 4.2. So on this side, I might eyeball more or less where that 4.2 might land, and that is okay. So if I eyeball that 4.2 to be about right there, I'm going to have my circle. This one's open. So this needs to be fewer than. It doesn't say fewer than or equal. So there's my boundaries, and the numbers are going to that are going to be the solution here are the ones that are true for both, which is everything between. So you see how this kind of mimics that. You know, it's everything between these values, everything between these values. The solutions are in the middle. Your variables in the middle. It includes this side, but it does not include that side. Okay. All right. Try one more. On number 4, it says a number C is more than negative 4 or, so this is another or statement, at most negative 6.5. So let's go ahead and write that one out. So it says a number C is more than negative 4. So let's write that one. C is more than means greater than negative 4. Or, we'll never combine and merge these together. They'll always stay separate. And so, or C is at most, which means less than or equal to that negative 6.5. And that's exactly how we would leave it. It's really just writing the twin equalities with the letter, with the word or in the middle. And then as long as it's true for one or the other, we're okay. So we'll just essentially graph each one of these, but on a single same number line. Okay. A lot of this is in the negative, so I'm going to move the 0 over. 1, 2, 3, 4, 6. Okay, so all my negatives are on this side. And let's see, so I'm interested in C values that are greater than negative 4. So here's negative 4. I'll go ahead and just graph that inequality. Everything greater than is always to the right. So that's one set of solutions that would make that whole compound inequality true. Or anything that is less than or equal to negative 6.5. So I'll locate where 6.5 is, which is probably, somewhere right in here between negative 6 and negative 7. Right? Or equal to, so we fill it in. And it's all the C's that are less than or equal to that. So that's going to be in this direction. So as long as it meets at least one or the other, anything in this solution set will work as a solution to the whole compound statement, and anything in this solution set will work in this compound statement because it doesn't have to be true for both. It only has to be true for one or the other. Okay, so all those solutions work. All right, so now that we know how to write them and how to graph them, how to kind of interpret whether it's an and statement and we want what's true in both, or an or statement where I want to know what's true for one or the other. Let's talk about solving, okay? So the big idea here is you can solve compound inequalities by just simply solving the two inequalities separately, okay? Okay, so we can simply just, easiest way, if you're not sure, you can always just solve one, solve the other, When a compound inequality is an and statement though, okay, and they write it together like as a single inequality, you actually have a nice little trick up your sleeve here. You can solve the inequality by simply performing those inverse operations that we've been practicing. Inverse operation. And just make sure, remember how we always say, make sure you do it on both sides. Well, this time we can do it on all sides. And you'll see what I mean by that. Okay, so on all sides of each expression. Okay, and probably of instead of on each expression. Okay, so the inverse operation. So let me show you what I mean by that. Okay, look at number 5. What I want you to understand is that you have two options here on number 5. So option number 1 is just to take each one of these and treat it as a separate inequality and just solve it twice, and get two different answers. So for a moment, I could just ignore that it's a compound, and I could take x is less than x minus 3. I'm sorry, 4 is less than x minus 3. And I could add 3 on both sides, and I could solve that inequality. And then I would come back up and ignore the left side and just do it over again here. But what I want you to notice is that when I solved the first one, I would have to add 3 on both sides here to get x alone. When I solve this one, I'm going to have to add 3 on both sides to get x alone. So what this second sentence is talking about, that when you have an and statement that's written all together like this, as a single compound inequality, you can essentially solve both of them simultaneously or at the same time by just making sure that you do that inverse operation that isolates your variable on all sides, and in this case that means all 3 sides. Okay, which is what I would have done if I did this one separately and then that one separately. We're just doing it together in one step instead of doing it in 2 separate steps. Okay, and that cancels out our 3, and so now I have 2 new values on the 2 boundaries. So on the left, 4 plus 3 is 7. In the middle, the 3 canceled, and so that's just an x. And then the less than or equal to is still there. And then on the right side, 7 plus 3 is 10. So it turns out that the solution to that compound and statement, that compound inequality, is all of the x's that are greater than 7 but less than or equal to 10. So that's the solution. And then we would graph that, and I would only be interested in exactly those values that are in between 7 and 10, because those are the ones that make them both true, right? So I might give myself some more room here. 6, 7, 8, 9, 10, like such. So I would have one boundary at 7, the other one at 10, including the 10, and my solution would be everything in between. Okay, so that would be the graph of all the solution, all of the x values that make that compound statement true. And I was able to do it. Now, if this feels just too weird to have sort of 3 quote-unquote sides to an inequality, then you can just take one at a time, solve that guy, find the answer. You're going to get, that x is greater than 7, and then go back and do the other side. You'll get that, and then you can either write the word and in between them, or you could write them together afterwards. That will work as well, okay? Now, number 6 is practicing the same thing, but this brings up that really important point that we always want to remember when dealing with inequalities, and that is that to isolate a variable, sometimes we end up multiplying or dividing by a negative, and when we do, we have to flip that sign for both of these. So we can still do these at the same time because it's a single, it's an and statement that's been written as a single compound inequality. There's my g. I want to get it isolated, so I'm going to get rid of the negative 5. If they multiplied by negative 5, the opposite or the inverse of that is to divide by negative 5 on all sides. Okay, and that's perfectly cool. That totally cancels out that -5. It leaves the g isolated and by itself. But because we divided by a negative, and this would have been true if I had done these individually as well, it doesn't matter. But because we divided by a negative, the inequality symbols have got to reverse or flip the other direction. That's the biggie here. Just don't forget that those inequality symbols are flipped, okay? Because now instead of a +15, when we divide by that -5, we have a -3. And on this side, instead of a -10, when we divide by -5, we get a +2, okay? So anytime you multiply or divide by a negative on both sides, or on all sides in this case, you have to flip those inequalities. So our solution is all the g's that are essentially between -3 and +2, including those boundaries, okay? So let's go ahead and graph that. Let's see, we'll do and then 0, 1, 2, 3. Okay, that should be plenty. So for our particular solution set, we're going to have a boundary at -3, and it includes -3. We're going to have a boundary at +2, and it includes +2. And the solution is all the g's that are in between. So that's everything between -3 and +2. So this would be the set of all values that make that compound inequality true. Okay, now that's awesome, and you can do that on and statements when they are written together as a single compound inequality statement, or statements are never written together, and in fact a lot of times they're not even the same equation. So that is not a tool you can use on OR statements. In an OR statement, you really are just doing two separate inequalities, and really the only thing that they have in common almost is that you're graphing them on the same number line, or basically that anything that makes either one of them true is true for the whole compound statement. But you really are working essentially two separate problems here. So be careful with that. Don't say, oh, I'm going to subtract 4 here, 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 all the way down. This is a totally different inequality on the other side of our OR statement. So here's our OR. And so you've got this inequality. It needs to be solved on its own and get the solution for that. And then you need to go back in and totally solve this one, which is going to take a different set of operations and get that solution. And then we'll say, oh yeah, well, anything that makes this true or that true is totally fine. So we'll graph them on the same number line. Okay, so let's take a look at number 7. Starting with the one on the left, z plus 4 is less than 2. To get z alone, we're going to get rid of that plus 4 with a -4. And that cancels the 4 there. It leaves the z by itself, and that's still less than. Remember, subtraction doesn't do anything weird to our inequality. It's only multiplication and division by a negative. So this is still less than, and then on the right side of this inequality, it's a 2 with a -4, which is a -2. So any value that meets this particular criteria is a solution to this entire compound statement, okay? On this side, I'll solve this one separately. We've got the variable here. They're multiplying by a -3. The reverse or inverse of that is to divide by a -3 on both sides. That cancels this. It leaves that z alone. I have to flip my inequality because I divided by a negative on both sides. And so that's now a z is greater than, and then -27 divided by -3 is a +9. Okay, so anything that makes this true or that true is then a solution to this compound inequality. So all I'm going to do in this last step is simply graph these together. And I wonder if I have enough tick marks. I'm actually going to go by 2's here because I don't know that I have enough to go by 1. So I'm going to go by 2's. I think I can handle that now that I've practiced this a bit. You would think I know what I'm doing, but okay. So I'm going by 2's there, 2, 4, 6, 8, 10. All right, and then I will graph each one just on the same number line. So all the x's that are less than -2, well, that would be an open circle on -2 and an arrow to the left. And then the other values that will also meet this criteria are any z values that are greater than 9. So 9 is right in here in between 8 and 10. Open circle there, and everything greater. would be to the right. So anything here or here will make that whole statement true. So that's our solution right here. Okay. Okay, let's try another or statement here. So on number 8, again, two different equations. You can see, inequalities, I apologize. So don't try to merge them. You can only really do that on the and statements that are written all together. Here, we're just solving essentially two different math problems. So we'll start isolating t here on the left by doing a -6, because that'll cancel the 6 they added. So now I've got 2t is less than, and I have a 4. And then to get rid of the 2, we'll divide both sides by 2. So for this side, we get that t is less than 2. Okay? All right, then we go to the other side. So or, right? And then we now solve the other side. So here's t. We're going to start off by getting rid of that 7. We'll do -7 on both sides. That leaves us with -t is less than or equal. And over here we get a -5. But then we don't want a -t. We got to get rid of that. So we'll divide by a -1. That's how we clear that sign, right? Because it cancels there. And now t is greater than +5. Why on earth did I flip that sign? Well, because we divided by a negative. So we have to flip that sign. So our solution here to this compound inequality is any t less than 2 or any t that is greater than or equal to 5. And then we graph that, and hopefully at this point y'all are starting to feel comfortable with that piece of it. Let's see, 1, 4, 5, 6, 7, 8. That should give us plenty. So we've got all the t's that are either less than 2 or greater than or equal to 5. And so there's our solution set. Okay? All right. So now if we feel comfortable with that, this is our last and statement. It's together, but it's a little more complex, and that's okay. You are welcome to separate it out if that makes it easier. If you feel like that's just, too much to handle to get it all done at the same time. But if not, you can certainly attempt to try to solve it all together as long as you do it to all, the inverse operations to all sides. Before that, though, we always simplify. So right now, what I want you to notice is that in here where our x is, there is a grouping symbol. They're doing 1/3 of all of this stuff. And so remember, our step 1, we talked about this, not even a night ago, is simplify both sides. No matter what we're doing, we always simplify before we start to solve. So right now, I'm not even going to worry about the -8 or the 12. I'm going to focus on cleaning this up in here by distributing that 1/3. And remember, multiplying by 1/3 is just dividing by 3. It's taking 1/3 of something. Okay, so when I do that, 1/3 of 6x is just 2x. Okay, and 1/3 of 24 is just 8. Okay, because multiplying by 1/3 is just dividing by 3. And this really got a lot nicer looking pretty fast here. Okay, so now it's looking a lot friendlier to us as far as math, and we're going to isolate that x. So we are going to start by getting rid of the 8 with a -8. But again, if I'm doing this all together, I just want to have to make sure that I do it on all sides. So yes, the 8 cancels, but it changes both of my boundaries here. On this side now I have a -16. Symbol stays the same. I haven't multiplied or divided by anything negative, so it still stays facing the same direction. And the 8 is gone in the middle, and on the right side, 12 and a -8 is a 4. Okay, and then in round 2, we come back in and we get rid of the 2. They're multiplying by 2, so we're going to divide by 2 on all sides, right? That's still a +2, so still no change there. We're doing -16 divided by 2 is -8. That is less than or equal to x, and that is less than or equal to 2. So that division gives us 8. -8, 4 divided by 2 is 2. And so there is the solution set that makes that whole compound inequality true. Okay? And then we graph it. Okay, so if we decide to go in here, graph this, this goes further into the negatives. So I'm going to scoot over a bit here so that it does fit. How exciting. So all my negatives are on this side, of course. Okay, so I'm interested in only x's that meet both of these criteria. So I have one boundary at add and including -8, and the other add and including 2, and my solution set is anything in between them. That is true for both of those. So it looks like that. Okay. Fantastic. Okay, let's do a word problem. A certain machine operates properly when the relative humidity H satisfies this inequality. Solve for H and find the range of values which makes the machine operate properly. So it's a nice word problem. It gives you some context, but really all we're doing is we're doing something similar to number 9 here, where we're solving this for H and getting the range of values that works here. Okay, so it is an and statement, and it's written together, merged together as a single one. So I'm going to take advantage of that, and I'm going to solve them together. But before that, we'll simplify the middle, because just like this guy here, there's a grouping symbol, and I need to simplify what's there in the middle statement. So when I distribute that, 2 times H is 2H, and 2 times a -50 is a -100. And now that the grouping symbol is gone and this is simplified, now I can really solve. So I'll start by getting rid of the -100 and by adding 100 on all sides. Okay, so I'll add 100 on every side here, and that'll cancel it in the middle. -60 and a +100 is 40. I still have 2H. The 100's gone, but I still have 2H in the middle statement. And on this side, 60 plus 100 is 160. Okay, and then in round 2, I go back in and I get rid of the 2. So instead of multiplying by 2, we'll do the inverse, which is divide by 2 all the way across. And that cancels the 2 there. 40 divided by 2 is 20. Symbol is still facing the same direction. I have not divided by any negatives. And in the middle, I have just an H now, and the symbol still a less than or equal to over here. 160 divided by 2 is 80. So this represents the range of values where this machine operates properly. Okay, so the machine is going to operate properly. We'll say that. So the machine will operate properly for values between 20 and 80 inclusive. And inclusive just means it includes those endpoints. It's got the or equal to. So that would be your solution. Okay, so the machine will operate properly for values between 20 and 80 inclusive, meaning it includes those endpoints. Anything outside of that, the machine probably wouldn't work very well. But this gives you a good example of sometimes there's a lot of scenarios when we use compound inequalities. All right, so that's part A of lesson 2.5.